Welcome viewers to this episode on hydrogen part 2, and it is the second episode on the topic hydrogen of unit 9 of class 11th chemistry book part 2. You must be remembering that in part 1 of this series of programs, we discussed the position of hydrogen in the periodic table, occurrence of dihydrogen, that is H2, isotopes of hydrogen and preparation of dihydrogen. In continuation to that, in this episode, we will explain the physical and chemical properties of dihydrogen, uses of dihydrogen and various types of hydrides. So, let us have a quick look at the physical properties of dihydrogen. Dihydrogen is a colorless, tasteless, odorless combustible gas which is lighter than air and is insoluble in water. Let us now explore the chemical properties of dihydrogen. The bond dissociation enthalpy for HH single bond is very high. In fact, it is the highest for a single bond between two atoms of any element. Thus, its dissociation is difficult, and at room temperature dihydrogen is inert. At a high temperature, in an electrical arc or under UV radiations, the dissociation of hydrogen yields atomic hydrogen. The atomic hydrogen has an electronic configuration 1s1 and it can combine with almost all the elements by either loss of electron to yield H plus ion or gain of electron to give H minus ion or sharing of electron, thus forming a covalent bond. Let us understand the chemical reactions in this slide which are exhibited by the dihydrogen. Now, first reaction is reaction with halogens. It reacts with halogens, that is X2, to give hydrogen halides HX. The example you can say is given for in the reaction fluorine, chlorine, bromine and iodine, all halogens react with hydrogen to give hydrogen halides. With fluorine, the reaction occurs even in the dark, and with iodine it requires a catalyst. Second reaction is reaction with dioxygen, and hydrogen reacts with dioxygen to form water. The reaction is highly exothermic, and you know that it requires a catalyst or heating. Hydrogen and oxygen combine to give you water, and the delta H enthalpy change for this reaction is minus 285.9 kilojoule per mole. Reaction with dinitrogen. With dinitrogen, hydrogen reacts to form ammonia, and it requires high temperature, high pressure and a catalyst as shown in the equation, and the delta H, that is the enthalpy change, is minus 92.6 kilojoule per mole. And you know that it is a method for manufacture of ammonia by the Haber process. Coming to the reaction with metals. Reaction with metals, with many metals dihydrogen combines at a high temperature to yield the corresponding hydrides. That is, M here symbolizes any metal and MH tells you that hydrides are being formed. So, reaction with metal ions and oxides is little different. Dihydrogen reduces some metal ions in aqueous solution and oxides of metals also, which are less active than iron into their corresponding metals, and the reactions involved are H2, and here we have taken the example of palladium ion, which is getting reduced to Pd solid, and we are getting 2 H plus in the aqueous solution. And similarly, we have represented the oxide of the metal by MXOY, which is a solid we have shown, and reaction of that with dihydrogen, that is YH2, gives us metal again to the reduced state. Reactions with organic compounds, it reacts with many organic compounds in the presence of catalysts to give useful hydrogenated products of commercial importance. For example, hydrogenation of vegetable oils using nickel as a catalyst gives us edible fats, that is margarine and vanaspati ghee. Second reaction is hydroformylation of olefins, which yields aldehydes, which on further reduction can give us alcohols. And here the two reactions are shown. First, hydrogen plus carbon monoxide plus olefin giving us the aldehyde, and in the second reaction dihydrogen is reacting with aldehyde to give us the reduction product, that is alcohol. Let us now see the vast uses of hydrogen. The largest use in the hydrogen is in the synthesis of ammonia, which is further used in the manufacture of nitric acid and nitrogenous fertilizers. In the manufacture of vanaspati fat by hydrogenation of polyunsaturated vegetable oils such as soya bean and cotton seeds. In the manufacture of bulk organic chemicals, especially methanol, that is dihydrogen reacts with carbon monoxide in the presence of cobalt catalyst and methanol is obtained as a product. It is also used in the manufacture of metal hydrides and also in the preparation of hydrogen chloride, which is a highly useful chemical. In metallurgy, it is used to reduce heavy metal oxides to metals. In atomic hydrogen and oxyhydrogen torches used for cutting and welding purposes, dihydrogen is also used. It is used in rocket fuel, in space research and also in fuel cells for generating electrical energy. Dihydrogen gives more energy per unit mass of the fuel consumed, and also there is no pollution by this fuel. And we will discuss more about this, its usage as a fuel in the later episode in this series, that is hydrogen part 4. Let us next consider hydrides, which are binary compounds formed by combination of hydrogen with other elements except noble gases. Hydrides can be classified into 3 categories, that is ionic or saline or salt like hydrides, that is the first category. Second category is covalent or molecular hydrides, and the third is, that is metallic or non-stoichiometric hydrides. Now study all of these classes of hydrides one by one in detail. So, ionic hydrides first. Ionic hydrides are stoichiometric compounds of dihydrogen formed with most of the S block elements, which are highly electropositive in character. However, significant covalent character is found in the lighter metal hydrides such as lithium hydride, beryllium hydride and magnesium hydride, and in fact beryllium hydride and magnesium hydride are polymeric in structure. They are crystalline, non-volatile and non-conducting in the solid state. However, their melts conduct electricity and on electrolysis liberate dihydrogen gas at the anode, which confirms that existence of H minus ion is there in the melt, which is shown in the equation below. H minus in the melt liberates hydrogen gas and 2 electrons go to the anode. Saline hydrides react violently with water to give dihydrogen gas. Sodium hydride plus water gives us sodium hydroxide in aqueous solution plus dihydrogen gas. Lithium hydride is unreactive at moderate temperatures with dioxygen or dichlorine and is therefore used in the synthesis of other hydrides, and these are shown here. It reacts with aluminum chloride and diborane to give us very useful compounds, which are lithium aluminum hydride LiAlH4 and lithium borohydride LiBH4. Now coming to the second category of hydrides, that is covalent or molecular hydrides. These are molecular compounds formed by a combination of dihydrogen with p block elements, that is CH4, NH3, H2O and HF are the compounds formed by the p block elements, and here CNOF are the p block elements. These are called hydrides for convenience in spite of being formed by non-metals. These are volatile in nature because they are covalent in nature. Molecular hydrides can be subdivided into 3 categories depending upon the relative number of electrons and bonds in their Lewis structure as electron deficient, electron precise and electron rich hydrides. So, coming to the electron deficient hydrides, as the name suggests, they have less electrons for writing Lewis structure, and examples are diborane, that is the common example, and hydrides formed by the group 13 elements of the periodic table. These are electron deficient, hence are electron acceptors and act as Lewis acids. Second category is that of electron precise hydrides. They have required number of electrons for writing Lewis structure, and examples are methane and hydrides formed by all elements of group 14. These have tetrahedral geometry. Electron rich hydrides, they have excess electrons present as lone pairs, and the examples are ammonia, which has 1 lone pair, water which has 2 lone pairs, and HF has 3 lone pairs on the fluorine. These are the hydrides formed by elements of groups 15 to 17 of the periodic table. These hydrides are electron donors and act as Lewis bases. These form hydrogen bonds and associated molecules, as is commonly known to you by the case of ammonia, water and HF. Metallic or non-stoichiometric or interstitial hydrides. These are formed by many D block and F block elements. Metals of groups 7, 8 and 9 do not form hydrides. In group 6, only chromium forms hydrides, that is CrH. These are non-stoichiometric, being deficient in hydrogen, and some examples are given here. You can see that hydrogen is lesser than in the proportion required by these hydrides. These are called interstitial, as hydrogen was thought to occupy interstices in the metal lattice without changing its basic type. This was so for the hydrides of nickel, palladium, cerium and actinium, but other hydrides had lattices which were different from that of the parent metal. Some of these metals, for example, palladium and platinum, could accommodate a very large volume of dihydrogen and could be used as high storage media. Thus, these were useful in catalytic reduction and hydrogenation of compounds. Thus, these have a high potential for hydrogen storage and as a source of energy. We hope that you found this episode explaining the physical and chemical properties of dihydrogen and the nature of various types of hydrides very interesting, and the concepts explained have been clearly understood by you. Let us summarize what we have learnt in this episode. Dihydrogen is a colorless, odorless and tasteless combustible gas which is lighter than air and is insoluble in water. The hydrogen-hydrogen bond enthalpy is very high and atomic hydrogen is produced at a high temperature or by UV radiation. Dihydrogen reacts with halogens, dioxygen and dinitrogen. It also reacts with metals, metal ions and metal oxides. Its reaction with organic compounds in the presence of catalyst gives useful hydrogenated products such as ghee by hydrogenation and aldehydes by hydroformylation, which give alcohols on further reduction. The reaction of dihydrogen with metals yields hydrides, which could be further classified as ionic or saline or salt-like hydrides, covalent or molecular hydrides, metallic or non-stoichiometric hydrides. Each of these categories had its characteristic features and reactions. In the next program, we will discuss about a very important compound of dihydrogen, that is water, and there we will explain the physical and chemical properties of water as well as hard and soft water. We will also describe the temporary and permanent hardness of water and the methods of removing hardness. But before you leave, there are certain questions for you which you can answer. How is hydrogenation of vegetable oils carried out at large scale to produce ghee or edible fats? What are the conditions used for obtaining ammonia from dihydrogen by Haber process? What is the percentage of dihydrogen used in the hydrogen torches? Explore about the uses of lithium aluminum hydride and lithium borohydride. Find the structure of non-stoichiometric hydrides. Thank you learners for watching this episode.